Yes. So good afternoon, everyone. Omar Islam, I'm a neuroradiologist, head of the Department of Radiology at Queen's University in Kingston, Ontario. Welcome to the AI and Radiology Lecture Series. We have a really exciting event lined up today, and as the advertising that went out for this event says, we have two titans in AI and radiology, and I think after we hear their talks, I think you will all agree that this was definitely correct. So I don't want to talk too much. I'm going to introduce our panelists first, and then we will dive right into our two talks. So first of all, in the middle of my screen, we have Dr. Amber Simpson. Dr. Amber Simpson is a colleague of mine here at Queen's University. She's the Canada Research Chair in Biomedical Computing and Informatics and Associate Professor in the School of Computing. And she's very excited about this, and so are the rest of us. She's the director of a new Center of Health Innovation here at Kingston Health Sciences Center in Queen's University. So welcome, Amber. And to my left, there's Dr. Anjum Ahmed. Dr. Ahmed is Chief Medical Officer for AGFA Healthcare, and he has been steering AGFA's healthcare innovation strategy for enterprise imaging and AI. And he's joining us from Brussels right now. So welcome, Anjum. And to my right, we have Dr. Jaron Chong. Dr. Jaron Chong is a radiologist in London, Ontario, at the University of Western Ontario. And he completed a Master of Health Informatics in the Institute of Health Policy Management and Evaluation from U of T. And he's currently the chair of the Canadian Association of Radiology's AI Standing Committee. And he's joining us from London, Ontario. So welcome, Jaron. So I'm going to introduce our first Titan. So Dr. Matt Lungren is here. He's joining us from Palo Alto, California today. Dr. Lungren is principal for clinical AI and machine learning at Amazon Web Services. He also holds affiliate positions with UCSF, Duke, and Stanford. So prior to joining AWS, Dr. Lungren was an interventional radiologist and research faculty at Stanford, where he co-led the Stanford Center for AI in Medicine and Imaging. His NIH and NSF funded research focused on multimodal data fusion models for healthcare applications, new computer vision, and natural language processing. He has served as an advisor for dozens of early startups and large Fortune 500 companies in healthcare AI go-to-market strategy. His work has resulted in over 100 scientific publications and papers, keynote talks around the world, and he's been featured on popular news outlets such as NPR, Scientific American, and Vice News. He's also a top-rated instructor on Coursera platform, and the course that he runs, Fundamentals of Machine Learning in Healthcare, has been completed by more than 10,000 students around the world. So we are extremely honored to have him here today as one of our speakers. And Dr. Lungren, the floor is all yours. Thank you.
Well, that's very, thank you so much for having me here and the kind introduction. Like I said, it's always nice to have such a warm welcome. Makes all the bad things that happen in my day over the weeks and all wash away. So thank you so much for that. Yeah, so I guess, I'm going first today, and I think that it's interesting, hopefully you guys can frame shift a little bit, because the things I'm going to talk about are at the end. So we're going to kind of work backwards, I think, in this particular session. And as you can see from the title, we're going to talk about what I've been calling, and I think a lot of people are calling, not just me, of course, but the day two problem, which is sort of how do we get these things into practice, and then what happens next? What do we need to think about? I think in general, I think a lot of you are familiar with the things that we do to affect different parts of the radiology lifecycle. Those of you who are in the imaging space recognize that many of these little categories I've listed here are opportunities in places where both research and commercial interests have found automating various components of this workflow effective, right? And we're still seeing what the true impact of some of those things will be. This is what I kind of call the radiology-centric view of this. Then we've also seen some pretty interesting things that have started to come up, which are opportunities to kind of do shortcuts around this. And I only show this to say that there's a ton of innovation happening around image reconstruction, as many of you may know. And also in this space, we're trying to term it opportunistic screening, which is something that allows us to take data and provide insights from that data that maybe human experts can't do, or they don't normally do. And then even now that we're starting to see new workflows open up, maybe we can actually bring some of those insights directly to the point of care. So this is where you kind of move outside that radiology ecosystem, and we start thinking about opportunities where the things that we're building may actually go outside of radiology. And there's some examples of that, of course. And so I just show this as a broad overview. We're not going to do any deep dives on this today because my talk is going to be about what happens next, not necessarily each of these individual things. But overall, none of these concepts I'm introducing should be terribly surprising to you if you've been in this space. Another thing that shouldn't be surprising, despite that we're seeing some economic turbulence, I think, in a lot of these areas, is that there still isn't a huge amount of investment in particular in radiology AI, right? And this is an older slide, but clearly we're seeing massive investment. And that really, believe it or not, has continued, again, despite some of the trouble we're seeing in some of the other verticals like crypto and other places. And really it's because the medical imaging tends to have, at least right now, the biggest traction more broadly and certainly globally for some of these solutions. And I like to call this my clown card slide, and sort of, obviously a little bit in jest, but you've been out there, you've been to the conferences, you've seen that there are many, many companies, so that investment has certainly borne some fruit, and we're seeing, each of them trying to find their place in the market and where they belong in terms of in our practices, right? Where do they fit in, and how does that work? Again, this is just another example where not only are we seeing the solutions, but we're also, and this is not meant to be read, obviously, but it's just to give you a bird's eye view of the different, at least in our country, the FDA cleared solutions. These are finding opportunities to really get, again, some level of a stamp of approval that this can be used in practice. So that's really setting us up. But where are we going to start to get into some trouble? And that's where this talk really starts to kick off. And this is something that came up in our group many years ago. And what we started to notice, that probably due to the availability of data, or maybe even a superficial view of what we do in radiology, we have focused an enormous amount of our effort and time and solutions on the pixel data for the study in front of us, right? We've tried to treat this by and large as just a typical computer vision task in a lot of these solutions. And that's fine, right? But anyone in the room here that's a radiologist recognizes that, well, that's not all I do, right? You mean you're probably saying that to yourself. That's not, how is this a fair comparison, between humans and machine? When I actually do something a little bit different, I'm actually using more of my training, and I'm actually looking at the context. And that's the next thing, right? So what is the other thing we do? Well, we look at the picture, but we also understand the clinical context, age, demographics, other diagnoses, right? The circumstances that surrounded the reason for that imaging examination. Well, there's data there, right? And there's opportunities to leverage that data, at least from the human perspective, and obviously now more so from the machine learning perspective. But by and large, that has been left out of a lot of the solutions that we're seeing come across. And from our lab, and many others have done similar work, and this is taken mainly from other verticals like self-driving car that looks at multimodal data sets. We've tried to show that you can actually fuse pixel and non-pixel data together to help get you to something that more closely resembles the work that we do as radiologists cognitively. But another thing that we do is we compare images over time, right? Again, talk to any radiologist who can think back to their first few months in radiology. They remember that the one time when they thought they had a diagnosis and they were so excited and they told their attending, like, well, did you look to see if they had a prior imaging examination? Of course you do that, and you realize that the entire situation is now different, because maybe that lung nodule that you thought was a lung cancer, well, it's actually been there for 5 years and it hasn't changed. That's important, right? Or that head bleed that you discovered is really just the same head bleed that's been imaged every single day for the last 5 days. Those kinds of things are critically important, but we're not considering them at the moment in the vast majority of the solutions we're putting out there. And that limits the clinical utility, and certainly something that we need to solve. And there have been groups that have worked on this. In fact, looking at Siamese neural networks as one example of being able to say, I can look at the difference between these two images and use that as a new data point to help, again, try to get to the cognitive work of radiology. And then the final thing I'll just mention here is that we think we're physicians, right? We go through all this training. We can offer treatment recommendations. That's part of our job, right? We're collaborating in many cases, particularly on difficult cases, with the clinical team. This is not an area that's been explored really much at all, but there is now work looking at multidimensional feature space, right? Can we look at our patients and their aggregate data as vectors in a new kind of dimension to say, listen, I think you're going to be heading towards patients like this actually end up going to surgery and having this outcome. Those are kind of the precision medicine ideas that have been floated around. Nothing really has gotten any real world traction yet, but this is where we need to go. And all that is to consider when people say, listen, Matt, there's a ton of investment, there's 50 companies, I have friends that have AI in practice, aren't we there yet? And I often say, you're here, right? Like you're really at the end of a bridge that isn't done yet. And we need to figure out how to finish and complete this bridge as a community. Some of this is going to require research. A lot of it's going to require folks outside of research to really make this happen. And I think it's important to understand that, again, all the things I've just talked about, the massive investment, the existing solutions, the opportunities in mirroring the cognitive work of radiology to get us closer to that, still are going to run into some fairly significant barriers. First of all, it's choice. There's a lot of models out there. A lot of them do the same thing. How do I know which one's the right one for my practice or my population? Do we go build it in-house? Do we go commercial? How do I know which one is better than the other in any given circumstance? These are things that we still aren't able to answer. And the second piece is the validation. We don't really have the infrastructure yet in a sophisticated way to say, well, I'm going to validate this on my practice. Where does it work? Where does it fail? On more than just a superficial level, but actually understanding, well, it does well in this particular subgroup, but actually for this group, it actually doesn't do well, or this type of machine or whatever. That's not really completely clear yet either. But the last piece is what we're going to focus on, which is integration. This is not as easy as hooking a couple things up or installing a new software program. This is gonna be much more than that. This is a stochastic discipline. This is not a very static piece of software, and we're starting to recognize the error of our ways to some extent as we're seeing these things kind of play out in practice, and that's what I'm going to focus on today. So the way I frame this, and hopefully this is somewhat familiar to you, is that you have these steps, right? You're building a model. These are the things you typically do. You're evaluating them in your practice. You're feeling like you're ahead of the game. You've productized it. You've tested it out. You've stress tested it. You've had your radiologist say, hey, it caught a lot of the head bleeds. I'm feeling pretty good about this. And you deploy it. And you deploy it in your practice. But what happens next is the critical piece that we still don't have a lot of understanding around. And that's really this monitoring observability. So that's going to be the theme today. And I think if we walk away with anything else in your head, is just that the end of the story is not that you've deployed it and successfully got the software up and running. It's actually what happens for day 0 to day N. What's our understanding of the ongoing performance of this model, and what kind of mechanisms do we have in place to get that information? And I love this graphic to help bring us into the same headspace. This is from a group called Evidently.ai. Great. It's an open source, but small company. And they focus on this idea of MLOps, observability, monitoring. And I've kind of taken this to the hospital space, which is that we have definitely mechanisms in hospital IT to say this software is working, it's not crashing, right? But it's all these other things that come up with ML models, which make them different, which we don't really have great mechanisms to monitor. And actually, that's really where the crux of the problem is starting to show up. When you have a problem with a model and you talk to your hospital IT and they say, well, I don't know why you're having a problem. It's working for me. It's clearly up. It's not down. It's all these other things that can affect the performance of a model that we aren't really thinking clearly about, partially because we haven't had to deal with this before, but also partially because this is still an unexplored area of science in terms of monitoring computer vision models. And I love to use Netflix as it's kind of the gold standard, but anyone who's used the Netflix service, which is a massively sophisticated machine learning algorithm that helps you decide, or helps, I guess, predict which movie you might like or how you want that movie to be presented to you based on your constant interaction with it. That is actually built on a very, very sophisticated ML ops approach. A platform, they don't just release one model and that's it, right? They're constantly updating. In fact, up to 1,000 times a day, they might be monitoring, finding changes and updating that model. And so what I like to say is that currently we have, we update a model that helps you decide which movie you want 1,000 times more than you do for a model that is trying to tell you whether you have an emergent head bleed, right? So there's something wrong that we need to address. And we've kind of taken this up over the last couple of years as something we'd like to start working on. So we started by saying, hey, listen, this is not a problem just to medical imaging, this is a problem across the industry. Aren't there other solutions out there we can use? And there are, right? There are many different solutions out there that can do this kind of thing. However, it can't do it in under a few circumstances. For the most part, it can't do it in a computer vision approach, right? A deep learning model. It's typically meant for tabular data, random forest, explainable type models. But the second and probably most critical point is that these tends to need contemporaneous ground truth. In other words, it needs to have that constant feedback of was I right or not in real time. And we can't do that, right? We can't do that right now in medicine. So we looked at this and said, okay, if we can't be taken off the shelf solution and there really isn't anything for us, what are we going to do? Well, we can break it down. We know that we can tell you if it's working, if there's latency, if we're having spikes in compute, that we can do. It's these other two questions that we need to figure out how to answer. Is the data coming into the model the data that it's expecting to see? And are the predictions that the model is making, are they accurate? Now, those would sound fairly simple on its surface, but I'm going to get into why they become more complicated when you really start to look at it. And when we started, again, to spend more time on this translation piece than the model development piece, we started to learn a lot about things like drift, outlier detection. And there's a ton of literature in this space, which is great. But how do we take those learnings and those tools and use them in our space? And that's kind of what we started to do, I want to say probably in 2020. When we started really saying, listen, we're seeing some performance changes when we do our audits. What is happening? And the conclusion we ultimately came to is there's no one doing this. Like there was no prior research. We couldn't just say, okay, well, they used a ResNet, we're going to try that, or a DenseNet. There isn't that intellectual arbitrage anymore that we've been benefiting from in this field. We actually had to come up with something new, which is kind of daunting, a little bit intimidating. But when we kind of said, okay, well, let's just start simple. What is it that we need to accomplish? We need to know what the model has been trained on. In other words, what does the model know and what is it comfortable with? And then how do we do a comparison from what it knows to what it's now seeing in real time? And making sure that those two things are similar enough that we don't have to worry that the model is now drifting or moving off its axis, right, to actually potentially underperform in ways that maybe we can't tell. And again, because we don't have the ground truth, that comparison is problematic. So in other words, if I knew immediately, or if I asked every one of my radiologists and I expected them to be 100% accurate, if I asked them to say yes or no on every AI decision, first of all, no radiologist has the time or wants to do that. But the second piece is maybe that radiologist isn't right, or maybe it's actually wrong or right for the wrong reasons, for example. These are the kinds of scenarios that we have to be guarding against as these things scale across massive populations. So we've decided to say we can break this down into three pieces, all right? So we know what the medical imaging data looks like, generally speaking. We have the input data, and that's typically from the DICOM or the pixel data. We also know the distribution of the predicted probabilities. So if my model was trained on a data set of, let's say, 15% were pneumonia, and it's typically running at, let's say, 15 to 20% of the studies it's seeing is pneumonia, if that was to significantly change, is the population changing? Is something else going on? Or is it actually a function of the model changing, right? And those are some questions that we can start to answer with relatively simple statistics. But it's actually this middle piece where we need to actually find a way to understand how the model is representing the pixel data and compare it to the data that's coming in and saying, there's a difference here. It's actually focusing on, for example, some aspect of the way the image is presented. And it's actually far off from what it was trained on. That in that out of distribution space is incredibly important, as we learned in our own practice. And so the way we decided to do this was to say, okay, well, again, let's take the simple things first. The DICOM metadata, that's structured data. That's relatively easy from simple statistics to say, in aggregate, I know what my model understands about the DICOM data it was trained with, and I can compare it to what it's starting to see in, you know, small slices of time over as the model's running in production. That's fine. I don't need ground truth for that. That's already there. So that's one metric. The second metric, as I mentioned before, is at the very end. What is the general prediction distribution? And beyond that, what's the confidence of those predictions on average over time, based on comparative what it was trained on versus what it's seeing. Okay, now I don't need ground truth for that either, because I'm just looking at the statistical difference over time between what the model's seeing and what it knows in terms of prediction distribution. Fine. Those two are pretty good. We actually did that fairly quickly. Then it came down to how are we going to actually understand what the model has learned in the network and compare that to what the model's now seeing in a way that's not disruptive. And so the way we took this, we actually went towards the outer distribution literature and found that a variational autoencoder would be a great way to reduce the number of features and allow us to do relatively simple statistics, because we created as we kind of treat it as a feature reduction problem. And when we did that, and because it was a variational autoencoder, you have these sort of Gaussian, it's not a point, it's actually a distribution, we were able to make some really great statistical comparisons. So then we can add these three metrics together. And you notice at any point in that this little description, I haven't said I need the radiologist to tell me if it's right or not. That's what we're trying to avoid. We're trying to find an automated way to see whether the model is still acting the way it should. That's all we're trying to do. And if it ever drifts outside of that, then we need to ask for human intervention, and we need to do something about it. But in the meantime, if it's still seeing things that it understands from our perspective, we can be confident that it's still working okay. And so we call this thing check stray, right? So this is just kind of how we, you know, and this is all open source, by the way. Feel free to check out the paper, download the GitHub. The code's actually pretty clean, so it's not messy. No offense to grad student code, right? It's actually production level code. We're pretty proud of that. We spent a lot of time on it. And what we're hoping to, just with this proof of concept, to show you is that these metrics, if you have access to the training data, you can create a model that does its prediction, as anyone in this room would know, but also you can create a monitor with that same data in the same way without, again, needing any sort of new UI. You don't need to make sure, you don't need to, hey, I don't know if that radiologist is any good. I don't want to trust them when they say the model's not right, or, you know, this so-and-so just doesn't like the model. They're always saying it's wrong. Like, this is completely no touch. And we're able to produce what we're calling this multimodal concordance metric that we can track over time. And our main goal is to say, is this a surrogate for ground truth, right? So if we actually knew the truth, how well does this thing that we're producing with our fancy statistics, how well does that actually track over time with real truth? So that's the experiment we needed to do. So this is what we did. We took a data set that was over time that we had ground truth answers for. This is a chest X-ray data set, pretty simple. We trained a model. And so on this part over here, this is just how it's doing over time. It's, you know, AUC is like 0.9 something. Great. That's great. So then at this point, this time point, we decided to purposely perturb the model in various ways. And there's a whole list of ways we did that. But in general, we reduced the performance of the model by 3% in this red, and then 10% in this line. Okay. So we're actually causing the model. This is ground truth, by the way. We're causing the model to do worse. Okay. Then we said, let's take our metric and see how well it overlaps, right? Because if this is if this is what's happening in real life, we wouldn't actually have the ground truth. So let's see how well our metric can actually track against that. And we found that in the 3 to 10% range, we could be triggered enough to say, hey, we can throw up a flag and say something's wrong. We can typically track it back to the general area of the problem. And we can say, you need to do an audit, or there's been a drift, there's been a change. You bought a new X-ray machine that was by a different manufacturer than the training data. Something's different. And then that's all we wanted to do. Just give me something that can be sensitive enough that tracks with ground truth that can give us an answer. So this is kind of how this would work in a cartoon fashion. Is, listen, I have this metric. I check it every so often, just like you run a phantom every day at your home institution for your CT scanner. I just want to know how it's doing over time without it having to do any intervention. Great. So now if I see this drop, I can actually do a deep dive, and I can say, let's hold on a second. Let's figure out now, between the training distribution, which we know, and what we're starting to see, where are these things different? And so now I'm starting to see on the machines, you know, for example, on the machine, right? My manufacturer header is different distribution now. Maybe you acquired a new hospital, you bought a new machine. Or maybe there's a pandemic, right? Now you're seeing a spike in pneumonia. Well, that's something you'd still want to know about, right? Because your model wasn't typically seeing those kinds of distributions. Or the general confidence of your model. The confidence of your model has changed. Being able to look at those individually is critical. And especially as we're starting to deploy these things and just kind of let them go forever, right? We don't have a trigger, right? Maybe some people talk about audits, great, but how do you know when to audit? You're going to get a bunch of radiologists to stop the model and do another ground truth test set so you can figure out how your model's doing. That's a lot of work, right? That's a lot of intervention. So this is kind of moving us towards that space where we can do a low touch, no touch metric that can tell us how are we doing in real time. And again, you start to get fancy. I've obviously made, this is fiction, I'm just being clear, but this is what I want to see where this goes. I want to be able to actually look at my prediction analytics. I want to be able to track my various models, and I want to have tabs that have the ability to look at both the drift and I guess we're calling here the black box shift detection or that pixel change. And when there is a change, I want to be able to look at it. And finally, I want to have metrics on my test set. So I will audit. Maybe I'll audit every quarter. When I do that, I can check both my performance over time against ground truth, but I can also check how has my concordance metric been looking over time too, right? But it gives me a place to start. And that's kind of been our big thing, because when we see these things deployed at scale, there's no way to know if it's going completely off the rails and you just didn't have any way to check. You may have had a couple of radiologists say it looks a little funny. What does that mean to you, right? We need to have actual data that we can track. So that's kind of the idea. And so that's the day two problem. We sort of say, you've hooked it up, you're feeling great, you've deployed, you're all high-fiving each other. And then what you do is like, what happens now? And the answer to that is, well, we think something like this, right? We're trying to work towards that space. And so maybe someday we'll get to the Netflix and we'll be allowed to retrain our models and do other things like update it, right? But until that time comes, we at least need to know when it's not doing what it's supposed to. So that's all I got for you. Hopefully it wasn't too much on the end of the line instead of the beginning of the line for the beginning of this session, but I really appreciate you having me here and listening to what I had to say. Thanks so much.
Great, thank you very much.
Thank you.
Omar, do you want me to take questions now?
Yes, please go ahead.
Okay, so I see we have a question, haha. So this is the question that always comes up about AI replacing radiology. So how do you answer that question now, and how did you answer it 5 years ago?
Is this the question about autonomous driving versus radiology?
Yeah, or, do you think you're going to be replaced?
I mean,
has your opinion on that changed?
I really hope so. I feel like I'm working too much, right? I still do clinical work. It's but I think in all honesty, there will be opportunities to carve out pieces, but in terms of it fully autonomous, I just don't see it with our current technology. Yeah.
And has that answer changed over time?
For me, it really hasn't completely. I think, but to your point, though, I think when we very first started, that whole idea of what is the cognitive work of radiology, we weren't thinking about that. Like, we were just like, hey, cool, this is awesome. It's like copying what I do. It's doing really well, or it's doing as good as my expert. So yes, I think initially I probably would have been mildly more optimistic, but I think as we've started to think more critically, and this is what's great about this field, is it's causing us to look at ourselves too, and really think about the work that we're doing that we kind of take for granted, right? The things that are brainstem for us, and how do we map that into a machine learning approach? And so it's actually, I love that part of it, but to the extent that, hey, it's not gonna know whether that bleed is new or old. That's something a human would probably be able to, you know what I'm saying? So there's things like that. You're kind of like, that's an easy one, right? Where it's not ready for quote unquote autonomous. The one point I'll quickly make, though, is that when I showed that first slide where I said that there's these point of care clinicians that are starting to want to leverage these tools, I think there are still opportunities there to not necessarily replace a radiologist, but to take pieces of things that we would have in a long report, break that out and probably put it into another place that's actually going to have them able to act on the findings quicker or more convenient for the patient. And that's something that we think about a lot. And we've actually done a clinical trial in that space. So watch that area. Certainly it's going to be radiologists are involved in that process, but are there things that we can actually give directly to the point of care again, not replacing radiologists, but just giving them what they need to know to do their job, and we take care of the rest.
Great, thank you. I'll ask one last question and then I'll pass it back to Omar. What are your thoughts on some of the bias in imaging AI work that's coming out of, for example, Zaid Obermeier's lab? What are you thinking on that?
Yeah, we work with Zaid quite a bit. We also you may have seen our recent work. We did multiple centers that looked at race detection, which is scary and fascinating at the same time. We spent almost 2.5 years on that project. Each of our labs would try to refute what the other lab was finding. We literally was like it was 7 labs. It was crazy, huge project. We never thought it was going to end in the way it did. But ultimately we couldn't answer the question of why it was happening, which is kind of strange for us. But what it does reinforce to me is that we need to have a really detailed understanding of where these models, how they perform in every subcategory that we can probably think of, right? We can't just approve it, say, oh, it does, on average, it's like 0.95 AUC, it's fine. Well, how does it perform on African-Americans from, disadvantaged zip codes? Or how does it perform in, overweight men from where, we have to know some of these things, both in our data sets, but also in our models. And the FDA, at least in our country, is incredibly interested in that. And I think that the approval process is going to look a lot different from both that perspective, but also for the monitoring. You need to have a monitoring plan, because these things, as I'm showing you, they don't go off the rails like, wildly all the time. But when they do, we don't have a way to know that. And that's something that, and by the time you find out, it's already too late, right? Because this is happening at scale. And so I do think that we're going to see regulatory bodies really push hard on this space, both from the bias perspective, but also how are you doing? Like, I'm just checking in, like, how is your model doing? The answer is, I don't know. I'll check, it seems to be fine. That's not an answer that we want to hear from an automated machine, right? So.
Great, thank you. Omar, back to you.
Yes, thank you, Amber. I just want to make a quick comment as well. One of Dr. Lungren's early slides, he talked about the role of the radiologist, and it's not just finding that bleed; it's what happens next, and where that bleed come from, so I'm in the same opinion that there is no way a machine at this point could replace a radiologist. And just to give in Canada, for those of you who are joining us from Canada and are radiologists or other specialists, there's a thing called CANMEDS rules, Canadian Medical Directives for Specialists. And there's 7 directives which are monitored and tracked by the Royal College for a physician and what they need to do. And medical expert is one of them, but so is communicator, collaborator, manager, health advocate, scholar, and professional. And so unless and until a machine can do all of those roles, which I don't think it's ready to do at this point, I think that, I'm going to answer that person's questions from Toronto, that I think we should all be safe in our positions for now, at least. Jaron, do you have any comments on that? Another radiologist, and
I'm really happy with the topic as well of the post-market and the data drift, right? Because I think just anecdotally, I've heard that discussed quite a bit, especially with the COVID-19 models in the last kind of like 1 to 2 years as well too. There's so much attention based on that. We saw some performance, we saw like a failure to generalize, and now there's the counter swing where we have meta-analyses talking about maybe the performance wasn't as good, and it just goes back and forth in cycles. To Matt, I have a very specific question. I appreciated the pun in the chest X-stray. So that was brilliantly named. I think that was amazing, right? And I love the way that you framed it with respect to temporal changes of a model that's deployed. And I wanted to ask a slightly related question to this, which is that in speaking to vendors, especially in the market that Rad AI is right now compared to what it was maybe 4 or 5 years ago as well, one of the other issues, which is not often phrased commonly, is drift from when you have a model with a production performance versus you're about to sell your first 10 customers, right? And what I often find with a lot of these AI vendors is, well, you come in with a paper, you come in with a performance of, it's going to detect bleeds at this percentage rate, and then the natural response from a clinical radiologist is, okay, well, let's install it, run a 3-month trial, see how it does, right? And you have that credibility dropped. Now, if I reformat your temporal model drift as a drift from what the vendor had originally proposed to that was first 3 months of deployment as well too, do you have any evidence that says that this drift in the fundamental feature vectors that you're deploying can predict that actually this model will not work well at this particular population or hospital?
That's an awesome question. First of all, let me just quickly call back to the COVID example, because you're exactly right. For those of you conceptually, just think of it this way. If you had a model, and this happened, right? Model that predicted your mortality from a chest x-ray in March of 2020, and you try to use that model today, you're going to have a problem, right? Because now we have vaccines, we have drugs, and things have changed. And so that actual change is a form of drift, just to conceptualize that, because I think that's a great use case, and thanks for bringing it up. Yeah, so in terms of, can we use this as a system to get a surrogate metric for the performance in a absolutely. One of the things that we had talked about is maybe folks don't want to use that or find that could be problematic. One of the things that we've actually also talked about was two-way encryption. So because you don't care about how fast it happens, which, as you know, it's about 100 times slower, but I can actually run encrypted inference. So I have a data set, they have a model, and I could actually have several folks from the vendor side, because several folks in the same space, deploy on my data set. No one sees either side. I don't see their IP. There's no installation. And when I do that, I can actually get a ranking, right, of actual performance on my test set, how they did. I think but to your point, I think that just as a sanity check, you could potentially say, just let me see the distribution that you have based on the 3 points that I had, and then let's see what it looks like if it saw my data. But obviously that still requires some sharing. I think that this is an area where I think it's going to be increasingly important, as you're pointing out, because there's so many vendors, and again, you sometimes don't know how well it's going to potentially do on your data till you try it, right? And by then you're kind of pretty far down the road. A lot of people invested time and effort, and then everyone's disappointed, right? And that's not what you want. So it's a great point.
Thank you. Perhaps I see there's a few other questions in the comment box, but Amber, you might get to those after our second speaker, if we have some time. So I'm going to introduce Dr. Alex Wong, the second of our two titans. So Dr. Wong, who's a professional engineer, is currently the Canada Research Chair in AI and Medical Imaging, member of the College of Royal Society of Canada, and co-director of the Vision and Image Processing Research Group, and professor of Systems Design Engineering at the University of Waterloo, which is in Waterloo, Ontario, Canada. Dr. Wong is a leading expert in AI, particularly in skin cancer, prostate, and lung cancer imaging, cardiovascular imaging, and microscopy. Dr. Wong is also the co-founder of Darwin AI and Lucid Labs, and a member of the College of Society of Canada. He has published over 570 papers in leading journals and conferences, and he holds over 30 patents and patent applications in these areas. He's the editor-in-chief of the Journal of Computational Vision and Imaging Systems and founding member of the Waterloo AI Institute. He's received numerous research awards at conferences and organizations, including the Ministry of Research and Innovation and the Imaging Network of Ontario. His awards also include a UN Top 10 Global AI Project recognition, Ontario Early Research Award, and over 25 Best Paper Awards. And his work has been featured in over 300 media outlets from around the world. So we are very pleased to host Dr. Alex Wong for the second of our two AI talks today. Dr. Wong.
Thank you very much. Thank you for the invitation to give this talk. For me, I was actually more interested to hearing what Dr. Lungren was talking about. Hopefully, tough act to follow. So hopefully I'll have something that's complementary to what he's talking about. And just talking about some of the validation, trust and so on and so forth, that I guess stems from some of what he was talking about. I'll probably have to ask Pam for a certificate as well, now that I've attended Dr. Lundgren's talk. And I will now get started. So related to that other question, people asking is like replacement of radiologists. My mentality is why? Like why? Like what's the main purpose when we could build tools to help improve? It's all about augmenting intelligence. At least that's my mentality. And so what you'll see during my talk is that's the kind of mindset that we take to our research. So I'm just going to try to share my slides And please let me know if you can actually see it.
Yes, we're good.
Okay, perfect. So the main focus of my talk, I think would be, it's very complementary to what Dr. Lungren was talking about, is for me, it's about the path towards trustworthy AI for radiology, right? So how do we actually trust these AI systems that we build? And I take it from a very engineering perspective, but also with a lot of collaboration with my clinical and radiology partners. So as Lungren mentioned, as you see in the media all the time, there's been huge amount of advances and promises in AI for radiology. You have like Siemens AI Rad companion being used right now. You also like in AGFA, there's Ruby for AI, where the underlying goal is, can they actually help radiologists unveil new information, as well as make their job easier, as well as improve consistency improvements. On my side, been doing a lot of work on the notion of radiomics, especially discovery radiomics, which is, can we identify sequences and information to characterize disease better in a quantitative way? And so related to this, I know there was just a bit of talk about COVID AIs. One of my main projects during the last couple of years was on COVIDNet, which is a global deep learning initiative for COVID-19 clinical decision support. And the key focus there has been on driving the innovation and research, and hopefully we could gain new insights into what are some of the limitations, as well as some of the innovations that can drive for not just this, but a number of different diseases. Right, and so it's an open source, open access project. Here's the link to it. And as to what Dr. Lungren as well as Dr. Chung had kind of alluded to, is things get outdated over time. Things change, behavior change, public health measures change. And so what we've done is we've continuously improved and updated models as well as data over time. And it's very fascinating to see the demographic changes, the types of biases that change over time, especially from the beginning of the pandemic all the way to the current stage. It's just really fascinating. It actually started off with a really simple project to help my student to really understand medical imaging. So started as myself as well as my student. Now we have a large team of over 50 different individuals working on various aspects. It's one of the most widely used open AI models of its kind for COVID-19 in the world for research purposes. Used by, I guess, researchers and scientists in all continents. We're actually quite happy to be able to help push innovation along. And what we did was we started off with things like detection, as well as risk stratification from just radiology. And we've since expanded to a much broader range of clinical decision support tasks, as well as provide open clinical integration tools, things like PACS integration and so on and so forth, as well as clinical decision support platforms for visualization, for getting inference information and predictive information. So we've been very fortunate to receive a lot of support from different people. And for me, one of the most gratifying was going to a conference and having a grad student come to me and thanking me for helping them with their thesis by providing this kind of resource. So as an educator, for me, that's the most important. And so just as part of initiative, really good, we have 8 different main initiatives, from open data sets to things tackling for detection, severity assessment, for both CT early on, then CXRs, ultrasound, as well as different approaches for survival prediction, AKI prediction, so on and so forth, as well as a ML-SIS model that integrates all of the AI into a single platform that people can plug in and use it as a research platform. And so the other key thing was just more related to data. As we mentioned, data change over time. And so one of the things that we initiated as part of this was to push what we call COVIDX, which is one of the largest open access data set of its kind, with data from 17,000 plus patients across 51 countries, from different views, different imaging systems, portable, fixed, different positions, supine, upright, across different age demographics. It's very fascinating to see how the demographics change during the COVID period, where it slowly moved from more elderly down to the younger, as well as also providing multimodal data, which is related to what Dr. Lungren mentioned, where it's not just images, right? There's a lot of clinical data, there's biochemical data, images, and so on and so forth. And so providing this source, the hope is to be able to drive innovation by having diversity and generalization. So my talk really isn't focused on this, but some of the lessons that we learned when doing things like that. In engineering, in computer science, a lot of times people think of AI as just take data and you dump in it, right? Magic comes out and you make predictions and it's gonna work all the time. For those with experience in this area, that just doesn't work, especially in the realm of in the clinical realm. And in particular, having worked with a lot of radiologists, clinicians, and so on and so forth, even if it was 100% correct all the time, based on initial tests, are they going to believe it, right? Chances are not really. Personally, I wouldn't, right? So why don't we use AI all the time, right? And the biggest thing is, one of the biggest challenges is just leveraging AI for clinical school. One of the biggest problems is trust. Right, and that's really the main topic that I really want to drive home. You can build all the fancy models in the world, but if you can't trust it, you don't understand what's going on, it's all for naught. So examples of where trust breaks down, on the left-hand side is a very popular example being used in the States. They're building an AI model for predicting who actually should receive additional care, and what they found, and it was actually being used for hundreds of millions of people, and what they found was that millions of individuals of, I guess, African-American descent were affected by racial bias, right? They just received less treatment, and when they actually went to look at it, what they found was it's because the inherent data was highly biased. Traditionally, historically, the Caucasian demographic received more care and received more funding. Therefore, by inference, the AI learns it. So one of the things I always like to drive home is AI is like a child, right? With my children, if I teach my child the right thing, that's what they're going to believe. If you teach them biased information, they're going to think it's correct. And now there's been a lot of, I guess, intention also in the area of where trust breaks down in the sense of adversarial attacks or adversarial machine learning, where people are finding that there are ways to actually cheat the system. For example, working on adding noise, adding attacks to data, so that when it's actually being diagnosed by a clinical decision support AI, it actually makes the wrong decision. And people are thinking, investigating they might be used for fraudulent transactions. Saying, hey, this patient really, requires a treatment when they really don't. And so these are the kind of things that I've been looking into, which is how do we actually get past some of these trust barriers? And in the old days, when we're talking AI companies, they're always like, let's wait and see. Right? Well, I think we're okay for now, but now it's no longer a wait and see kind of situation, especially in really mission critical systems. Things like the Canadian Digital Charter, C11, the European Commission's AIA Act, where there's big fines, as well as global revenue penalties, as well as the FTC now saying, we could hold you accountable, so be ready or we'll do it for you. And so now this kind of compliance and trustworthiness become very critical, not just as a wait and see, but as a global must. And so this all sounds very, terrifying. So we should never use AI, right? Like, why bother? We can't trust it. Well, that's not really the point. The point I'm trying to drive here is that by thinking about these kind of problems, we can actually really push significant advances and progress towards ethical, responsible, trusted AI, especially in the realm of clinical and radiology. And so key thing I'm going to talk about here is what are some of these technologies and I guess initiatives that are being out there right now for helping to improve trusted AI in applications such as radiology. I'll be talking about 4 key things. One is quantitative explainable AI, which is why does the AI actually make that particular decision? Right, as Dr. Lungren alluded to, right, it makes a prediction. We can look at the underlying statistics. Can we actually dig deeper and say, okay, great, what is the rationale behind the decision? Then there's the notion of trust quantification, which is when can the AI be trusted? Where are the biases? Where are the gaps in the actual trustworthiness of the decisions it makes? And this gives you a much better sense of trust because you have a lot more transparency into how the system works than the notion of improved medical imaging modalities. A lot of people kind of forget about it when they learn AI, garbage in, garbage out. So when you have better modalities with the data that you need, you have better trust in your system. And of course, best practice as well as ethical considerations. How do you actually design trustworthy AI in the first place? So just a quick primer for those not quite acquainted to the notion of explainable AI. Here's just, based on the DARPA's definition. Really today, we have a lot of AI models that are largely black box systems. So it'll give you a recommendation, give you a decision, but why do you do that, right? Why not something else? right? Why do you think this patient has this and not that? When do you succeed? When do you fail? When does the AI just give you nonsense, right? When can I actually trust the opinions of an AI? As well as the most important for me is how do you correct it, right? If it's a problem, what is the inherent problem that I need to fix? And so what we've been focusing on is the notion of explainable AI in the sense of being able to understand why it made a decision, why it didn't make another decision, when it's actually doing well, when it's failing, when I can actually trust the decision it makes, where are the limitations, as well as know where the error came in so we could fix it in an actionable way. And so the approach that we've taken, and that has been quite successful for us, is from the notion of quantitative explainable AI. We've all heard the term QXAI millions of times. You see a billion different heat maps. Here's a little darker, here's a little lighter, you know, positive, negative, blah, 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 blah. But then the question is, how do you move from theory to actionable insights, from proxy to direct explanations? If I gave you a heat map, okay, great. This looks a little brighter. So maybe that's more important. How much more important? Did it actually influence the decision? If I don't use it, is it going to think of something else? Right? And so it's not quantitative, and it's pretty much, it's like me telling you something and just, oh yeah, it's based on my speculation, right? So with quantitative explainability, the underlying goal is, can I actually identify and provide an explanation that tells us exactly what are the key factors leveraged in making a decision, as well as the quantitative justification as to why. So in a very simple example, here you have an image of a jet plane. In quantitative explainability, what it does is here, because looking at the jet plane, it's because of the front, the nose, the cone, as well as the wings. And the reason is because of these visual factors, the model actually predicts that it's a warplane with 98.7% certainty, because otherwise, and that's where the counterexample, the model would just, if I rely to other information, it's going to think it's a parachute with 23.5%, right? Similarly for the meerkat, by looking at the face, as well as the chest and nothing else, I can actually determine, the AI can determine it is a meerkat with 97.4% certainty. Otherwise, it actually thinks it's an ostrich, right? And so for me, as well as a lot of people I work with, this gives them a much better sense of, oh, this is the thought process that went through with the AI, and these are the actual visual indicators, because we know for sure concretely that because of this, it drives that particular decision. So it goes from speculation to qualitative to quantitative and more definitive. And so, great, we have this concept. What use is it, right? What's important about it? Well, there's actually very, very good use cases for quantitative explainable AI. One of which that we've heavily leveraged is ensuring that the right decisions are made for the right reasons. Right? Which is, can we make sure and validate it during the AI design process, as well as the evaluation process, that it is in fact making good, sound decisions. So here's an example of a lung disease severity model. There's actually two different models where we're able to reveal, using quantitative explainability, that exactly this honeycombing pattern led to this particular decision. On the right is a case for COVID where it is able to indicate that by looking at this, ground glass opacity, it knows that it is COVID with a certain amount of certainty, right? And again, it's shifting from having a bunch of colorful heat maps that gives you speculative information to saying this led to decision because otherwise I don't think I would make the same diagnosis. So another important thing is, great, verifying that it makes the right decision for the right reasons. Another one is identify reasons for wrong decisions. And this is something that I always try to remind students, that when you're building AI, make sure it's not using something stupid to make a decision. And that's where explainable AI, especially quantitative explainability, becomes very important. Here's an example of a case where a model is being built by a student, no problem with them. They were told that the data was pristine. Right, everything was there. We clean up everything, and then afterwards, what we did was we built the model, and well, the model was really doing poorly. And so what we did was we used quantitative explainability to take a look and see that apparently the model was producing misdiagnosis when there is embedded text present in the X-ray system. You really should not be reading this text in making a decision, especially wrong decisions. And so by doing this, what's the actionable insight in building your model? Well, let's get rid of it. Let's get rid of this text. And as soon as we get rid of the text, it starts focusing on the right things. Like, for example, in this case, it's a lung disease. You should look at the lungs, right? And so naturally, by removing this kind of distraction, it starts looking at the right thing. Another one that a lot of people don't think of is making sure detecting the right decision for the wrong reasons. A lot of times as engineers and computer scientists, they'll look at one thing or two things, which is accuracy, things like sensitivity, specificity, a number that summarizes how well it does. And for me, that is completely useless because I could have a perfectly accurate system, but it could be doing all the stupidest things in the world. So for example, on the left-hand side is a model that we did for, detecting COVID-19. Again, this is for like experimentation, for really exploring how AI thinks. And we trained it on CT data. And what happened was, first is like, wow, like great numbers, 99% sensitivity, right? 99% specificity. Most people say, okay, let's call it a day, let's publish a paper. But that's useless. What we did was we dig deeper and we did quantitative explainability on it. And what we found is that it's really, really great at detecting COVID by never looking at the patient's lungs, right? Like, it's like, wow, like that blew our mind. Every single case, what they were looking at was the type of patient bed they were lying on, right? This is just ridiculous. And so a good indicator that, at least at this stage, AI will not come close to replacing a radiologist. Good luck finding a radiologist that looks at beds to make decisions about lung disease. So here's a situation that also led to an actionable insight. What we did, to no one's surprise, we removed the beds. And guess what? It started looking at the right things in the lung. It's these simple things that quantitative explainability really allows for. On the right-hand side is also a case where we're working with, a particular, partner, and they said, our data is perfect. We had people hand clean every single aspect, right? And then what we did was, again, build a model. And this one, actually, a lot of people actually use this for contests. Like they get great numbers, they're fighting each other for prizes, so on and so forth. But what we did was we did analysis, and we found that all the models out there were useless. Why? Because they were using imaging artifacts to make decisions. Like in this case of CT, it's using the padding on the side to make decision on predictive analysis on severity of a disease. Again, all nonsensical, but gets swept under the rug without this notion of quantitative explainability. And we've since moved into the realm of second order explainability, which this quantitative explainability facilitates for, which is a bit meta, which is explaining explainability. So what if I have a lot of explanations for all the different types of data? Can we actually explain and identify key trends that led to a diagnosis for us to get more insights to that? So what we did here in this example of second order explainability was we looked at the core trends, concepts, and patterns leveraged by the AI to make decisions based on all the different explanations it gave for different data sources. So for example, what we found for one is, here's a severity assessment model. What did it actually look at? Not just the explanations, but across the board, what drove its decisions? It was like things like, ground glass opacities, it would honeycomb. So things that made sense, but now we're able to identify, okay, it's actually doing things that aren't incredibly stupid, not just for one case, but it's using similar kind of concepts as a radiologist would leverage. And so being able to provide this becomes very important. Then we went into the realm of trust quantification, which is less about why did it make a certain decision, but when can we really trust the decisions that it makes? And under different situations, does it make more trustworthy decisions for, let's say, African Americans? Does it make less trustworthy ones for people above the age of 65? And so having this really allows us to have a much deeper insight into, can we really trust this model under these kind of situations? And so as a result, what we did was we built this explainability-driven design framework, which always has a clinician in the loop, where through the discoveries made through explainability, we then get clinical consults say, is this clinically sound? Is it stupid? When it's stupid, don't use it. When it's clinically sound, which one is more important? And so this interaction with clinicians, with radiologists during the actual design process, not only improves the models, but also improves the data that we use to build these models. And so we've had a lot of success in building much more trustworthy, clinically relevant systems with proper sound rationale. Again, it sounds like I'm just stating obvious, but you really want to build models that make sound decisions or sound recommendations. So what are some of the use cases? We've used it for, COVID-19 screening, more from exploratory perspective. It really facilitate for the validation by clinical experts to ensure that the decision-making process is not just only correct, but also consistent with clinical interpretation. Really helps build a sense of trust with clinicians as well as healthcare workers. In another case for risk stratification, it allows us to not only validate the information, but it actually led to better performance because it allows us to work better with expert radiologists to examine data and really identify what visual markers are correct and what really shouldn't be used. Similarly, we did that case I mentioned before, where for fibrosis progression prediction, where everyone had great numbers, all of them were useless instances. What we did was we used this as a way to audit the data and to do QA/QC on the data. And as a result, the top what you see is what the model relied on to make decisions before. On the bottom is what they used to make decisions after this AI-empowered QA/QC process. Similarly, we did for clinical ICU admission prediction, where we're able to build customized, really tailored deep learning models predicting ICU admission, but it really provides both the actual explanations leveraged by the actual AI to improve the design. And not only that, by going through this AI explainability driven types of design approach, the performance actually went up. So we get better performance. It was a faster system. We understood what factors it leveraged, as you can see in the middle, as well as how trustworthy it is for different genders as well as age. And so we're able to really balance how it performs across the board. Then, like I said before, beyond just really understanding how they make decisions, it's really about how do you actually improve the data it goes in. A very important recent NIST report came out, which I really appreciate, was they had this part which breaks the myth, saying AI isn't magic. You don't dump data in and it magically knows what, it's like garbage in, garbage out. If the information is not there, then it's not going to find it. So improving imaging modalities can really greatly improve the trustworthiness as well as the reliability on AI. So one project we've done recently was for prostate cancer. It was in the middle, what you see is like a T2 weighted image. There's a whopping cancer, can't really see it well. Again, train an AI, it's not really going to do too well. So what we did was, well, let's come up with a new modality called correlate diffusion imaging, which gives you what you see on the right, which is much more concrete, visible, as well as localized data about the tumor itself for margin estimation and for building more effective AI. And so we've been quite happy in leveraging, again, better data to do it. Last but not least is best practices and ethical considerations. Everything I talked about so far was just technology. Technology doesn't solve all the problems. You really need to think in your design process. Things like transparency, like I mentioned, explainability. Different AI models, different AI methods have different levels of transparency. You want to use the right one for the right task at the right level of transparency. Data provenance, AI is only as good as the data. Right? Know the limitations of your data. Bias, this is the obvious one. Identify, test, and mitigate them as much as possible. Data leaks, right? I showed you before, AI was using random stuff, things like black bars for padding, image, watermarks, and so on and so forth. Really be able, especially using things like quantitative explainability, to be able to identify it so that you can actually remove and mitigate these kind of problems. Class imbalance is a big one, right? Training data is often imbalanced. Knowing how to use it, how to train it properly becomes important, or else you have very serious ramifications. My favorite example that I have was there was a contest for skin cancer analysis. Everyone did amazing. Everyone's like 95%, accuracy plus, right? Then I looked at the data. Well, it's actually rare that people have skin cancer, right? So looking at the data set, 90-something% of the data had no cancer. Like, it's not a stretch of imagination. I could just build an AI in 1 second and say everything is benign, 90-something% accuracy. Is it useful? Absolutely not. These are things that we really need to think about when building AI in an ethical as well as correct way. So, final thoughts, right? AI really does hold great potential and promises for clinical decision support for radiology, but it's really about using it right to really support and augment radiologists in what they do. There's tremendous challenges to achieving trusted AI. We've made a lot of great progress, but there's still a lot of progress to be made. And I guess the message for me is the benefits really outweigh the challenges in operationalizing trusted AI solutions for enhanced clinical decision support in radiology, as long as you take the right mindset to it. So thanks everyone, and I will stop there.
Thanks very much. Does anybody on our panel have questions?
I do.
Go for it, Anjum.
Thank you so much. A wonderful talk, Professor Wong. And I absolutely agree with you, the concept regarding augmented intelligence. Now, you spoke about the data integrity. One thing that I was reading somewhere in regards to the generative adversarial networks, GANs, and they have been recently tested and used for creating synthetic data or to mimic the existing data sets. There's a lot of discussion around data hacks going on. And if a system is vulnerable, if someone is able to use these GAN networks and create or inject false findings into your existing data sets. So will it be possible for AI actually to detect some of these artificially induced clinical findings in images?
Oh, very good question. And for me, that's always the worry. Fortunately, one of my areas is in adversarial machine learning. So there's been a lot of essentially data poisoning approaches, like the one I mentioned, right? To give it false sense of data, making decisions just to, let's say cheat insurance. There's a lot of different, very hazardous approaches there. And one of the things that we've been also working on is not just adversarial attacks, right? We do it because we want to have a deeper understanding, but we're also building ways for adversarial defense, which is, as you mentioned, detecting these attacks going on, being able to flag it, being able to identify it. And what we found using explainability, we're able to identify these watermarks, these hidden aspects of it that actually led to the wrong decision. So there's a lot of effort going on right now for not just attacks, but also detection as well as defenses. And even in the case where it's not a intentional method for doing the attacks, I've also, because we've done a lot of open source, open data kind of process, making sure the integrity of the data that is being open becomes important, right? And so you see a lot of data sets. We put in extra effort to make sure that we create in the right way so that we're less prone to these kind of approaches. A good example is recently we did a quantitative explainability kind of analysis on ImageNet. What we found were things that just didn't make sense. For example, a fun one for everyone is that we're looking at, parachutes, right? Parachuters. What we found using our explainability was one of the key ones was apparently Superman actually snuck into the data set. So obviously it's a cape, not a parachute, but these are the key things that we sometimes don't pay attention to. Even if it's unintentional, they end up being kind of like data poisoning.
Absolutely. I think the way you explained it is it's easy to understand and comprehend. And I think from an industry perspective, I think that's where the focus should go towards also in the coming years, because as more and more AI systems will be deployed, this will become a sensitive topic and something to monitor.
Exactly. And for me, it's one of the key factors in being able to unveil these problems, or just to give better confidence, it's just the notion of explainability and understanding.
Do you think, maybe one last comment I want to make on this, do you think the quality and regulatory bodies should also be considering and focusing this? Because if you look at Health Canada or FDA in the US, they're focusing around data sets in terms of how the algorithm was trained and will be used for its intended use and purposes. But do you think this should be also brought into quality and regulatory discussions?
Most definitely. One of the things that we found as we were doing our various projects, of course, initially we were really focused on, models. Are the models good? But what we found is you can't really disentangle model from data, right? They're very intertwined. And what we found is that the more we did model validation, model building, as well as model explainability, we found that it ended up being data explainability, understanding the data, find a course, it ended up being a very powerful tool for a QA/QC, right? Again, garbage in, garbage out. And the worst part is that it's not in garbage, it's actually has a negative impact. That's the biggest problem. And so what we found, again, with explainability is that it gives us a level of confidence as well as a way to take actionable steps in building better models. So I definitely think people should be looking more into this.
Absolutely, I agreed. Thank you so much. Thank you, Amber.
Thank you. Jaren or Omar, any questions? Or Matt?
To Alex, actually, I just wanted to ask, taking a look at COVIDnet and just the open source database that you guys very quickly gathered and published, and I'm on Kaggle.com, my left window right now, I'm seeing it as well too. One of the things that's been constantly brought up from a Canadian researcher perspective, right, is the Canadian regulatory landscape, right? Obviously it differs from the US landscape, it differs from the international landscape as well. And the main comment that I get from clinical radiologists that want to participate in AI research is that the RAB component, the anonymization component, it makes it quite difficult, or is one certainly like a higher than average burden one would expect to participate in this research. So now that you've run actually a multinational data set collection as well, do you have any perspective on that in terms of what Canada is doing or not doing correct, and what things that we should be advocating for at a national level, or how do we change that?
So I really appreciate this question, because having been involved in doing this, I've gathered a lot of insights, mostly on things that we haven't really been doing well compared to other countries, which is our RAB processes. Like essentially, I'm pretty much like swimming in RABs. It takes a very long process. And again, in many situations, we've gotten such considerable support from radiologists, but there's such these huge barriers of entry compared to other places. So having a more streamlined process, I think becomes, I know there are certain initiatives, but I don't think it's streamlined enough to push a lot of research going. There's situations where, I'll just give an example. The worst case I had was working with a radiologist. It took 3 years to be able to get the data. It's not because the data is not available, it's because of the paperwork, to the point where the radiologist, I mean, you have better things to do than dealing with paperwork, right? Just lose interest, right? And so having a more streamlined process, and as well as a more open process, becomes quite important. So one of the things that I'm working on right now is, can we actually do something at the national level to push more openness in data access, data management, as well as collaborative ways to be able to share data in a way that enables research across Canada. So that's something I'm looking into. Will I succeed? I'm certainly going to try.
And the follow-up question to that is, in the other communities that you've experienced internationally, is there a group or an institution or another country that does it best in terms of balancing individual privacy rights with open access data? If Canada could copy any other country or any other organization, who should we copy?
Very good question. I think this one is something that Dr. Lungren can speak more about. I actually quite envy a lot of the efforts by the RSNA. Like, it's a much more unified process. People try to get together, do things. Here in Canada, things are a lot more siloed. Of course, there are other countries where, again, I envy the access to data, but they have access to data because really just their ethical considerations are less. So that's not really something that we want to kind of emulate. But I actually would like to turn this over to Dr. Lungren to speak more about some of those efforts.
Well, yeah, no thing. I mean, this is obviously, as you know, we're huge fans of your work, because you, particularly because of the data set work you've done. I think we've tried to take examples from as many places as possible, making the argument we try to make is, this is a public good, right? So, you know, the primary purpose has been served, the patient has been diagnosed, or whatever the initial purpose of it. Now it's sitting somewhere. And at least in our country, unfortunately, there is a massive enablement. So our HIPAA law, right, which we always talk about as our privacy law, there's actually nothing about privacy, and the P's don't stand for privacy. They stand for portability. Like, so it's actually a way to get the data out and still sleep at night. That's kind of the purpose of that law. And it's actually enabled a multi-billion-dollar industry well before AI was a thing, for buying and selling right data, and in terms of claims data and prescription data. In fact, anytime an American goes to anything related to medicine, your data is being bought and sold. And if you, as long as you remove those certain identifiers, that's okay. What we're trying to push is that on the one hand, we do have that laxity because of that law is actually relatively pretty nicely, preserved. But our problem isn't really the privacy argument, which is, some of it, but it's actually the folks that say, well, my data is valuable. I don't want to put it out there because I want to sell it to Google or whoever else out there, some company, or start a company, whatever. And we're really trying to make the case that if this patient didn't say explicitly, you may sell my data, there's some ethical uneasiness to me, I think, and people would agree with that. So if that's the case, if you still made it available, you can still enable amazing innovations. You can make, enable insights that benefit everybody. So the trade-off of the patient not knowing explicitly that you made that data available to whoever is outweighed by the potential benefit to everyone by having that data included. I think it's a tightrope that we walk, right, to try to make that argument. But our hope is that eventually we get to a place where the data that is made available is representative of the people that we're trying to build models and solutions for. Because right now, as maybe you've seen some of the recent work, almost all the data is coming from New York, Massachusetts, and somewhere in California. That's not representative of certainly of our country, and then across the world, right? That's ridiculous, and it is definitely observing some of the problems that we're seeing in terms of generalizability, no question. And then the biases, right? The bias discussion is driven by, as Alex said, to the data, right? So it only knows what the data you've shown it. The last point I'll make, though, is I think that the tide is turning to some extent, and I don't know, I can't speak specifically for Canada, but at least on the research arm, there's a lever you can pull. And if you're federally funded, which at least in our country is the badge of honor and is the thing we all aspire to in academics, is achieving academic funding from the government, from the NIH. They're starting in January, actually, 2023. It's no longer suggested that you make the data available. They're saying if you're funded by us, you need to make the data available. It's no longer like a, hey, nice to have. It's a must have. In fact, there's even talk of potentially pushing that further to say it needs to be made available openly and under these circumstances. Now, that is a big deal because there's 300,000, some odd researchers across the country, in fact, even internationally, that are funded by the NIH. That's a stick. It's not a carrot, right? We can't entice them with morality. We can maybe entice them with penalty, right? And so that's really part of the goal. I would also give a shout out to the UK Biobank, which is a tremendous effort. I mean, it's slow and somewhat difficult, but as you can imagine, when you start throwing genomics in there, I don't even know how comfortable I totally feel with that. But again, you're seeing some incredible data being put out there for biomedical research. So, but again, I think it's going to take a lot of individual efforts. First of all, to see the sky doesn't fall. Second of all, to see that the insights are made. And maybe thirdly, just from an economics perspective, we're commoditizing, we're kind of diluting the value of those that are holding the data back. And those that do that aren't really participating in the broader conversation around the solutions that we're building, which actually is a disadvantage for their patients, right, in some ways. So it's a balance, but nothing I've done in this space, and maybe you've had the same experience, nothing's been easy. And I've definitely lost sleep worrying that maybe maybe we missed something, right? You don't want to have anything bad happen because everyone's eyes are on this. And the email you never want to see is, hey, pulled up a chest x-ray and your data set saw a patient name. Like, that's end, right? That takes us back several years if that happens. So we're incredibly careful, but I do envision a future where I think the public good argument will win.
Well, these are things that we should learn from a Canadian perspective. I think there's some good Canadian open initiatives, but I think it could be pushed quite a bit more and finding just a good balance, right? Everything's about balance, right? It's not, hey, open everything and not worry about the ramifications, but it's also not about, let's just hold on to everything and treat it as kind of pretty much a pile of money that we redistribute. So for me, I mean, I'm going to try to put that effort in Canada and hopefully I succeed. Anyone who wants to support that, please contact me.
Matt, do you think we should move to a model of consenting all patients to data sharing?
That's a tough question. I get asked that all the time. I mean, technically, in most academic medical centers in the U.S., you actually sign one of those really long, like it's like, you know, iTunes. You just kind of just agree. You don't really, you know, it's several pages. And patient's sick. It's kind of like it was unethical to even think that you can consent to something in a lot of medical scenarios anyway, right? Because you're kind of like, I just need to sign, take care of me, right? I think that we always consent typically for research. So when we make these data available, which we've been criticized for, but we specifically say it's not for commercial use. It's not for clinical use even, because we don't really know. And as we've shown you, this could cause problems if you try to use this clinically, right? In a lot of scenarios. However, for research and education is what that's how we walk that tightrope. I think a lot of patients, I think this has been looked at in various surveys, and I don't have specific numbers, but I do think that my recollection is that it's a majority of folks would be like, sure, you know, use it for research and education. That's okay, generally speaking. I do think it does start to drop off when you talk about, well, now I want to use this to build a product, which is kind of like, we all know that we probably need that. We need that industry in order to deliver. I mean, my lab isn't going to make a beautiful UI and deploy something for you and go through all that. That's just not what we do. That's not the purpose we serve. And so we do need the commercial partners to make these things a reality. So how do we bridge that? I'm not sure yet. But there has been conversations around patient consent, and I have heard others in the field say, you know what, it's not even the hospital's data, it's technically the patient's data. And can we get to a place where we have patient-centric data markets, data control, and permissions? And I don't think that that's a bad idea. How do we get to the point where everyone's on the same page and believes the right things, and how many boxes will I have to click for exceptions, and also have the understanding to do so? I'm not sure. But either way, I'd love both models, in the sense that as a patient, I'd love to just be able to bring my data to all the different healthcare providers, at least in the US, who don't communicate, which would be amazing. But then on the other side, I feel like, you know, research and education should still be somewhat sacrosanct, because a lot of the things that we've both talked about today is only possible because we have that access. And putting that additional burden on us to do this work, we would be years behind, right? It just, the effort required for that.
Great, thank you. Any more questions from the panel? All right, I think we're just about at the end of this thing, Omar. So we've got another session coming up in the fall, right? We're going to pause for the summer, get some sunshine, and schedule a new one for the fall. I want to thank our speakers for coming. Omar, do you want to give a final thanks?
Oh, sure. So thank you to both of our titans again, Dr. Lungren from California and Dr. Wong from Waterloo. And of course to Dr. Anjamemad Chong, and to you, Amber Simpson. Thank you very much for being on the panel again, and Pam Moore for organizing all of this. Yes, we will be back in the fall, and likely end of September and October. Look out for social media and other email invites. And everyone have a great summer. Thank you very much.
Great. Thanks so much, everyone.
Sure.
Thank you.